Hello, and welcome to Remcom's webinar on touchscreen analysis. I am Jeff Barney, a product marketing manager, and I will be demonstrating this capability using the electrostatic solver that is built into XF. I would like to start out by briefly explaining what touchscreen analysis is. So consider interacting with the screen of your smartphone by tapping or swiping your fingers. There are rows and columns of conductors in the screen that are sensing where your fingers are based on the change in capacitance between the electrodes. I will be referring to those electrodes as driving and sensing lines, and touchscreen refers to the design of their shape and separation to more accurately detect finger locations. Once the geometry has been defined, a simulation can be run, and this will calculate self and mutual capacitance for the matrix of conductors, and additionally, electric field and voltage distributions can be seen. Further, touchscreen analysis can be used to design the lines in isolation, or a more complicated phone model and hands can be included. Now, I mentioned cell phones a couple of times, but this analysis applies to multiple other applications including tablets, digital cameras, and infotainment systems. Today, my plan is to cover the various features that are available with the electrostatic solver and show how touchscreen analysis can be performed. I'll start out with an introduction to XF's user interface and setting up the geometry, and then I'll show how to specify the drive and sensing lines so they'll be included in the capacitance matrix. I'll then show the simulations window and the options for creating a static simulation. And I've already pre-run a simulation, so we will have capacitance matrices and field results to look at. The fields will include voltage and electric field distributions throughout the space. I also have two projects that I would like to show that demonstrates the use of a more complicated model with a hand in the typing position, and then also a 1mm stylus and how its location can be parameterized. At the end, there'll be time for questions. So I'd like to start out with an overview of XF's user interface. This product has been developed at Remcom for a number of years, and one of our large customer bases is antenna design or mobile device design. Now, this is beneficial for touchscreen analysis because we're able to reuse a lot of the same functionality. Some of the important features deal with CAD import, so we're able to bring in multiple different file formats of fully detailed models. And you can also have extensive geometry creation capabilities where you can create geometry natively within XF. So this is the XF user interface. I'm going to go ahead and give you a quick overview of what's here. So on the left-hand side is the project tree, and this is where you can keep track of everything that's in the project. Of particular interest for touchscreen analysis is going to be the parts. So this is where you keep track of the CAD models, the shapes and sizes of the electrodes and the stack-up. Also of interest is the static voltage points. So this is where you're going to define which electrodes are going to be used for the capacitance matrix. And then you'll also be interested in these materials where you define what the electromagnetic properties are of the various parts in your geometry. In the middle is the geometry window, and this is where you'll do a lot of the CAD manipulation and specifying voltage points. The drop-downs across the top allow you to create geometry within XF, modify that geometry, or also modify any kind of imported CAD files you may have. This is a geometry window, so you can modify it or close it. And all of the windows that are available are on the right-hand side. So when it comes time to defining parameters, you'll come to the parameters window, or when we want to look at results or create simulations, there are also windows for that. In terms of the project that I'm going to be demonstrating today, it's going to be this 4x3 touchscreen. If we look in the parts, we can see that there are 3 driving lines and then also 4 sensing lines. There are 3 layers of dielectrics, so the upper, the middle, and the lower. And all of the electrodes are created as PEC materials, so as a good conductor. And then the dielectrics are all lossless and have a relative permittivity associated with them. I do want to touch on the more advanced capabilities of feature-based modeling within XF. So this is how we create geometry, and this allows us to start out with a very simplified structure. So here, this driving line was built by originally starting with an extrude. So we came in and defined a cross section, which was just this diamond shape. We then extruded it some distance, so a very small distance, just to give it some thickness. And then once we had that shape, we could then apply a linear pattern to it. So here we've taken the one diamond extrude, we've copied it 5 different times essentially, and the distance or the separation associated with it is also parameterized. So that's the diamonds. There was then the jumpers, or the bridges that were used to connect them, and those two pieces of geometry were Boolean together, so the end result is this single driving line. If we want to go back and make modifications to the original diamond, well, it will then propagate up to the full model, and since it's parameterized, we can come into our parameters window and we can change those parameter values and see how it affects the geometry. So here beta is being used to define the thickness of the bridges, and when I apply it, we can see that the geometry updates accordingly, and so this bridge is now 2 times thicker than the other bridge. The next point I would like to discuss is how to specify those driving and sensing lines so that way they're included in the capacitance matrix. We're going to do that using the static voltage points, and we're going to want to create one static voltage point for each line. So if I right click on it and create a static voltage point on parts, I can then come in and rename it, and if I want to associate it with the driving 1 line, well then I can just click and drag and drop it on there, and now we can see that the driving 1 line is going to be 1 row or 1 column in our capacitance matrix. Alternatively, I can select the geometry through here, so let me set this invisible so we can have access to that geometry. When I double click on it, it's going to open an editor up here. The first setting is just saying that yes, I do want to have the static point enabled. I'll give it a name, and then I'll just leave it at 0 volts, because when we run the simulation, it will properly account for the setting it between 0 and 1 in order to get the matrix. And then I can simply come in and click and select the geometry that I'm interested in. Once I've done that, I can expand these and I can verify that indeed the driving 1 part is associated with the correct static voltage point. The same thing with sensing 2. This next project addresses a slightly different stage in the design process. So here, all of the pads are separated out into individual parts, and the jumpers or the bridges are not in place. So this happens earlier in the design process when you don't have a fully complete model. And so what we're going to support here is the ability to select multiple different parts and have them tied together. So here I cannot select this one driving line and get all 4 pads. So whenever I come in and create a new static voltage point, what is this, driving 1? When I come in and edit it, I can use the control key and I can select all 5 of these pads, so that way they are then treated as one static voltage point, and they're all listed under here. So this is still going to treat it as though it was a complete piece with the bridges in place. So once those driving and sensing lines have been defined, well, then it's time to run a static simulation. For those customers who are familiar with XF, you're more familiar with the XFdtd solver. That's our full wave time domain solver. But for touchscreen analysis, you're going to be using the static solver. And this is an iterative method that solves at 0 hertz. So coming back to the user interface, let me go ahead and open another project so that way I can demonstrate how to set up the simulation when all of the static points are properly defined. So here we have the 7 points representing the 3 driving and the 4 sensing lines. And to create a simulation, I'll come into the simulations window, and instead of creating an XFdtd simulation or one of these other types, I'm going to be interested in the capacitance matrix. This will open up a window where I can enter some last minute information. If I was running a parameter sweep, I would start out here by adding a parameter or the various values I would like it to take on. For this example, I'm not going to run a parameter sweep. The next tab is going to be the capacitance matrix. So this is going to define which static voltage points you would like to include. And here I'm going to select them all, so that way we wind up with a 7x7 result matrix. The next tab is going to be the static solver, where I can enter some information about how many iterations I would like it to solve and when I would like it to stop. Basically, whenever it reaches this residual threshold, it says that I've reached a significant level of convergence and I can go ahead and end the simulation. And then the other thing that I'm interested in down here is going to be saving the static fields over the simulation space, so that way I can look at the field distributions whenever it's time to look at results. So I can go ahead and create that simulation and run it. When I do, it'll be added to the simulation window with some information down here in the summary about what the parameter values were, what was added to the various runs. Since I went ahead and ran this already, I can look at results and see that yes, the simulation is run. It only took 1100 iterations, and it took 1:45 to run. Once the simulation has been created and has finished running, well then we have the opportunity to look at results. And we do that in the user interface through the result browser. So if I come over to the results window, across the top I have 4 panes which allow me to filter to grab the specific result that I want. So here I'm interested in the full matrix simulation. I'm interested in the capacitance matrix sensor. And let's go ahead and look at the capacitance matrix. So here we have the 7x7 matrix, and the values along the diagonal are going to represent the self-capacitance, while the values in the off-diagonal terms are going to represent the mutual capacitance. XF reports those results in both the Spice and Maxwell formulations. And then the other type of result is going to be the field distribution. So here let me select a different simulation where I only had one driving line active. I'll select the static fields, and let's go ahead and look at the voltage. So when I double click on this, it's going to open up the geometry window, and I can see the voltage distribution within my geometry. So let me just change some of the viewing settings. So that way we're going to be looking in the XY plane. Let me also move it up. Okay, and then so now we can see that the driving line has been activated with 1 volt, and we can see how much coupling has transferred onto the other lines. I can also change the properties here of our scale bar, maybe to get a slightly better picture. Yeah, okay. So again, here's the active driving lines in red, and then we can see the coupling onto these 4 sensing lines. And this is what XF uses in order to determine those capacitance matrix, and then the mutual capacitance and the self-capacitance. In addition to voltage, we're able to look at the electric field distribution. So let me unload this, and instead of voltage, let's double click on E field and load that result. Again, let me go ahead and change what we're viewing. So that way we're going to see the electric field distribution, and here a slightly more interesting result about how the electric field is coupled onto the other lines. And then also, instead of looking at it in this type of view, we have the ability to look at a vector field. And so here we can see the vectors of fields as they're coming out of the driving lines and coupling down onto the other lines. So that's the results that are available, both the capacitance matrix and then also the field distributions. And so the last thing that I want to show is just a more complicated example of using a hand and a stylus to see what those capacitance results are given a more complicated environment. So I mentioned that one of the customer bases for XF is mobile device design. And that's beneficial for touchscreen analysis because they are also interested in how the performance of your device changes based on how it's held in your hand. So if you're typing on your screen, or if you're holding it in one hand versus the other hand, or if you're just using your finger to swipe the screen, well, then customers are interested in knowing how that affects their performance. And so built into XF is the ability to handle these posable hands. Now these are CAD models that can be imported and repositioned. And here we're looking at a typing position for a more complicated phone model. If we look at the static voltage points, we can see that there are, it's a 19 by 30 array of electrodes. And if we want to reposition these hands, we can go ahead and select one, right-click, and come into the Edit menu. From here, we have controls on each one of the joints. So if I select this joint here, or this portion of the hand, well, then I have controls that will allow me to move that hand or that thumb back and forth. And then at the end, there are more controls at each of the joints. So I can then move it up and down depending on what I would like. So that's the posable hands and how they can be used to test your capacitance for various holding configurations. And then also I would like to show a stylus. So here we have a stylus with a 1 millimeter tip. The stylus was built in XFdtd, so it was the tip was created from just a revolve, or a half sphere, and the tip itself, we've applied a translation to the end. And so this allows us to reposition it rather quickly and rather easily by just dragging and dropping it. Instead of specifying a specific distance of a translation, I want to go ahead and provide a parameter value. And so now the stylus itself is parameterized and can move back and forth by just changing the parameter. So if I come to the parameters window, instead of offset being 0 millimeters, I can make it 5 millimeters. And we can see that the tip then moves right along that edge of the electrode. And when it comes to creating a simulation, I skipped over this a little bit. I didn't show how to create the parameter sweep. But here, if I'm going to create a capacitance matrix, here I do want to perform a parameter sweep. The offset values are from 1 millimeter to 5 millimeters, and there's 5 increments. And so now when I hit create simulation, you can watch the stylus tip move 1 millimeter and have a simulation written for each location. At the end of this simulation, you will have 5 different capacitance matrices that you can then evaluate and check for its effect. So that wraps up everything that I wanted to cover today. We went over XF's user interface and how feature-based modeling can be used to build up your geometry. We also talked about how you would specify those driving and sensing lines, so that way you get the full capacitance matrix. We talked about the static simulation and how it's a little bit different than the FDTD simulation, and what are some of the settings that you need to specify. Once that simulation was finished running, we had time to look at the results, both the capacitance matrix, but then the electric field and voltage distributions. And then in the end, we just quickly went over some more advanced cases where we're looking at a more complicated phone model with hands, where we were looking at repositioning a 1 millimeter stylus. So at this point in time, I'd like to open it up for any questions and also provide our contact information for those of you that are interested in learning more about this feature or any of the products that we offer. So if you just give me a second, I'm going to check to see if any questions came in, and I'll be back to you in a minute. Thank you.